Thanks, Hans. So my name is Vincent Vanouk. I work on the speech technology team here at Google. And I thought I'd try to share with you a single piece of insight that we gained from working on speech technology at Google scale. And that can be summarized basically as such. If you want to get a shot at superhuman performance in machine learning, maybe the first thing you should try and do is to get rid of all the humans. And so you might be questioning my premise already. You might be wondering, I'm talking about superhuman speech recognition here, and we all know that speech recognition is not at human performance yet. The problem is that it's getting dangerously close. And let me just give you an example. Imagine, so one of our products is voice search. You can just speak to the search engine on a mobile phone. You can just talk to it. So imagine that you talk to your phone. We record that prompt, and then we play it back. We play it back either to yourself, or we'll play it back to the speech recognition engine behind voice search. Okay? And we ask for the transcription. There is no question at this point that you will do a much better job than the speech recognition engine at recognizing your own speech. The picture changes if you actually change this setup and play the audio to a naive human. And by naive human, I mean someone who doesn't know you, who doesn't necessarily have the same cultural references as you have, who doesn't necessarily live in the same neighborhood, doesn't have the same context. It actually becomes a toss-up. If you just play it once to a user and ask them to transcribe it, they will do almost no better than the speech recognition engine. So why is that? Roughly, without going into details, speech recognition is two components. There's an acoustic model and a language model. And the acoustic model is what recognizes the sounds. And we're not really at human performance yet in acoustic modeling. In fact, the fidelity is not yet at the level that a native human speaker would have. But we have this language model, and the language model is what predicts which words you're saying and which order you're going to say. We train similar to machine translation huge corpuses. We train on 240 billion words for voice search, and that gives us an edge that a single user might not have. So if your naive user, your naive human, is not from Canada, he might not know how to spell Saskatchewan. If a person is not from New York, he might not know how to pronounce Schenectady, New York. And I'm not even sure I'm pronouncing it right myself. But this edge really makes the difference. So why is that a problem for us? Humans really get in the way. Franz just mentioned that the human evaluation is a huge problem in machine translation. It's the same thing in speech recognition. The ground truth, the standard, the golden rule, the golden standard for speech recognition is human performance. We have humans transcribing these speech recognition, and that's what we benchmark ourselves against. And if the benchmark is barely better than the actual system, then we really have a problem. The other issue is that with the kind of growth that we've seen in terms of usage, we're getting a ton of data flowing throughout the system. Every day now we get about 2 years worth of data, and we couldn't even start thinking about transcribing all of that. And we also have to support 27 languages. Internationalization is a big emphasis for us, and we're trying to expand in all the languages of the world. So I'm joking here, but so Fred Jelinek is a very famous person in speech recognition. He used to say that every time he fired a linguist, the performance would improve. I want to fire all the humans. So the key insight for us has been that speech recognition, as I said, is two different components, and those two components try to sort of compensate for the deficiencies of each other. Right, so the acoustic model can compensate for deficiencies in the language model and vice versa. So the traditional way of doing it is you have the truth that's set by a human transcriber. That's the gold standard. And you benchmark your system against the truth. You compare your best system against the truth and trying to push it and learn towards that goal. If you remove the truth, you're out of luck. You don't have anything that you can compare against anymore. the trick here for us is that we can actually cheat, and we can artificially make it harder for some parts of our system to function. We can actually weaken parts of our system. So for example, if I weaken my language model, then I suddenly have a system that's actually less powerful, and I can compare against our best system so far. So if we train our system and try to improve our acoustic model based on that, we're going to get something better. And then we can basically do the same thing with the language model using a weakened acoustic model, and then improve our language models. The result is that we end up with a better system, hopefully, a better combination of the two that can become our gold standard, and we can iterate from there. So the message there is there are ways to do end-to-end development without having humans involved. And while unsupervised learning is not new, and it's been done for a very long time, having a completely end-to-end pipeline where you can do training, evaluation, tuning, entirely unsupervised without involving any human, at least in speech recognition, that's very new and that's very exciting. That's really the kind of things that we're really excited about, because it really enables us to scale at levels of scaling that we haven't been able to reach before. And so while we're not yet at superhuman performance, it's possible that by removing that ceiling of human performance, maybe that will enable us to get to that faster and that asymptote towards the actual human performance that we're seeing. So that was my bit of wisdom that we've been working on recently, and it's been a very exciting development for us, and there's a little bit more in the paper that I put it in the previous slide.